Hello everyone. Welcome to our webinar for the month of June 2025. My name is Ryosuke Okuno. I'm a professor in the Hildebrand Department of Petroleum and Geosystems Engineering. Before introducing today's speaker, I will briefly introduce the Center for Subsurface Energy and the Environment on behalf of our Center Director, Dr. Hugh Dego. The center is an organization of 27 faculty members who do research on all topics related to subsurface energy and the environment. So here are the key characteristics of the research conducted under the center. We work on various subsurface applications such as conventional oil and gas, unconventional oil and gas, methane hydrate, geothermal, CCUS, critical mineral extraction, hydrogen, and methane emissions and the fundamental processes. And the center covers a wide range of technical disciplines, including drilling, production, reservoir, petrophysics, formation evaluation, and also data analytics, machine learning, geomechanics, rock mechanics, geology, geochemistry, and sustainability. And we do experiments and also modeling and software development as shown on the right-hand side. And here's a list of current industry affiliate programs under the center. And if you are interested in any of them, please go to our website and you can find the details of the programs. So CSEE monthly webinar series is industry-driven and hosted on the second Tuesday of each month at noon. All webinars are uploaded to our YouTube channel within a few days. The upcoming webinar for the month of July will host Robin Domis from the Bureau of Economic Geology. And if you are interested in sponsoring the webinars, it's $5,000 per webinar, and sponsor's name and logo will show up in the webinar flyer at the beginning and end of the webinar. Live audiences include the industry, government, and academic professionals. The webinars will be posted on YouTube after the live event. Our webinar videos have been quite popular with over 14,000 views in the past 2 years. And benefit of a sponsorship include reaching a global targeted audience and associating sponsors' brand with high quality research and education through the webinar. So for more information, please contact Center Director, Dr. Hugh Dego. And today's webinar is going to be done by Dr. Omar Carrasco. He's a research associate at the University of Texas at Austin, has been collaborating with myself since 2021. He earned his PhD in material science and engineering from the University of San Luis Potosi in January 2020 and was awarded the 2020 Context Postdoctoral Fellowship, which promotes research partnerships between Texas and Mexico. His work focuses on energy conversions through photocatalyst and electrocatalyst, with a focus on hydrogen production, CO2 conversion, and carbon capture. With that, I'm going to pass the microphone to Omar.
All right. Thank you, Dr. Kuno, for the introduction. So, hello, everyone. My name is Omar Carrasco. I'm a research associate working with Professor Okuno for the past years. And I'm happy to present this topic that is called efficient carbon management via novel pathways. This is a topic that we've been working for quite a few years, and we have really exciting outcomes that I would like to share with you today. So in particular, I'm going to be talking or presenting the electrochemically driven bicarbonate separation and conversion. So before going into the slides, I would like to thank all collaborators for this project, which is a couple of graduate research assistants, particularly Ayush and Daniel from the chemical engineering department, and as well the collaboration with Professor Manish Kumar, as well from chemical engineering department. So this is a work that has a lot of efforts from many sides. So I'm happy to present as well and share all these results with you today. So as you may probably know, amine-based post-combustion capture technologies are very well-proven technology that has been commercially available for the past years, and it has been very useful to get to the targets, international targets for the decreasing carbon content in the atmosphere. So I'm going to go through the process, the conventional process, very quickly. So the CO2 capture emissions, they are being captured by using a specific amine solution. And then this amine solution has to be regenerated at the same time that the CO2 needs to be released from the amine capture solution. And this process is achieved through thermal treatment. Then this free CO2 or this purified CO2 is being compressed and then sent to the utilization unit which typically can be presented as CO2 electrolysis to produce different chemicals and products. So as I mentioned, this is the conventional way and has been proven to be effective for a couple of years now. However, this process is what I would like to call the CO2 catch and release, because we are capturing CO2 here and we are releasing. So we are working with the same CO2 phase, a CO2 gaseous phase. We use, as I mentioned, a temperature swing for regenerate the amine and release the CO2, which is quite energy intensive. So the values that are reported in literature is below 4 megajoules per kilogram of CO2 released, and this represent like a high cost or impact the cost of the overall technology with around the 60 to 80%. And as well, in addition, to this process, we have to include the CO2 gas compression energy. So we have many points that we can work with this conventional pathway in order to improve the efficiency of the process. So one of the ways that we've been thinking is if we replace the way that we are working with CO2. So instead of using CO2 gas, what happens if we use a liquid carbon-bearing product such as bicarbonate? So this will give us different benefits. In particular, I'm going to mention three. So the first one is the benefit for storage and delivering. That will enable to reduce the operation cost, the transportation cost. So since we are not using a compression, so transporting a liquid product is more is cheaper than or easier than the CO2 gas. And as well, by using this liquid carbon content a product, we are going to overcome the mass transfer limitation of using CO2 gas. So for instance, we have like a saturated bicarbonate solution can contain 100 times higher carbon concentration compared to an aqueous CO2 saturated solution. So this is one of the second benefits, and the other one is in this case, as I mentioned, the electrolysis as one of the main utilization steps. Talking about particularly about this electrolysis, we have this conversion. It's more energy efficient than producing the same product from the CO2 gas. We can save thermodynamically around 50% of the energy compared to the CO2 gas. So therefore, I'm presenting here our proposed carbon management pathway using bicarbonate to improve the energy efficiency of the carbon capture and utilization process. So in this case, we are going to be able to utilize the CO2 emissions in a capture unit. After this process, we are going to get bicarbonate produced, and this bicarbonate then it has to be separated from the capture solution, and the amine as well needs to be regenerated. So therefore, we will have bicarbonate that is going to be ready for utilization step. In this case as well, we are considering the same units or the same process operation compared to the conventional catch and release process. So um, in an overall way, this bicarbonate liquid product, once it is formed and separated, can be used directly as a feedstock, and we can also avoid the conversion step if needed. And as well as I mentioned here, we are not going to be using the temperature swing or the thermal regeneration process to separate this carbon-bearing product and for the amine regeneration. We can propose or we can study another methods like the electrochemical one that I'm going to present today. And this process can be done at ambient temperature and pressure. As well, we don't need to utilize CO2 compression. So that's also going to be beneficial for the cost operation, and as well we can get the similar products as if we are using the CO2 electrolysis. So in order to produce this bicarbonate from the CO2 capture reaction, we are working on developing specific amines. We are functionalizing tertiary amines to improve the CO2 dissolution in aqueous media and therefore produce bicarbonate. For the second step, for the separation and regeneration, we are exploring the electrochemical driven separation using a membrane-based technologies. We can separate bicarbonate at the same time and regenerate the amine at the same time under ambient temperature pressure. And for the conversion of this bicarbonate, as I mentioned, we are as well envision the electrolysis process to produce as well to convert this bicarbonate into many other value-added chemicals. So I'm going to introduce first some highlights about the CO2 capture as bicarbonate. As I mentioned before, the main topic is the bicarbonate separation, but I want you to have some preliminary information in order for you to understand the point of the bicarbonate separation and amine regeneration results. So for the amine development, as I mentioned, we are working with tertiary amines. This is the reaction for the amine with CO2. We are producing bicarbonate, and then we get the protonated amine. So this is the typical chemical reaction for a tertiary amines. For our study, we first utilize the DMAPA amine, which is a diamine composed by one tertiary amino group and one primary amino group. Each different amino group has different features. In particular, the primary amino group has been utilized and explored a lot. It is well known that the primary amino group perform faster kinetics for the CO2 capture reaction, and the tertiary amino group is particularly used for the bicarbonate generation. So what happened with this amine development? We are introducing a propylene oxide to this primary amino group over here to produce this surface active amine. We call it surface active amine, which is now this primary amino group is transformed into a tertiary amino group in the same molecule, but with this added surface activity, built-in surface activity that is going to improve the CO2 solubilization in aqueous media. And at the same time, we're going to be producing bicarbonate. So We have a study, as I mentioned, this particular diamine, the MAPA, and we have compared the introduction of these propylene oxide groups, and we have demonstrated that the bicarbonate production can be increased by 54% compared to just the tertiary amino group, in this case, the DMAPA. So as well, we have tested a couple extra features of this surface active amine, particularly this DMAPA. We have explored the stability of this surface active amine over consecutive cycles of capture and desorption. In this case, was the desorption experiments the desorption experiments were conducted just to stress the amine and study the stability and the bicarbonate performance. Although it was not initially the purpose of the surface active amine. But we also found that these amines can be used in a conventional way if needed, and performing desorption of the CO2 at lower temperatures as 80 Celsius. So, and also we have studied and we have observed that these surface active amines are stable over consecutive cycles, capture and desorption, with a constant or stable bicarbonate performance. And more recently as well, we are exploring different ways for the surface active amine. We are exploring different chemical structures. Right now we are from this diamine a molecule. We are also reducing and making more simpler, and we are presenting, or we are studying different type of amine, and as well we are studying the incorporation of the PO groups, and as well the different amount of CO2 concentration we are introducing. So we are starting from 100% CO2, and we right now we are studying diluted CO2 concentrations, and as well we are exploring the concentration effect of this surface active amine over these different conditions. So one of the key points is we are able to perform, or these amines can be used for experiments with diluted CO2. In this case, we are targeting explore direct air capture conditions, which we know the conditions are lower than this, but as I mentioned, we are in the state of exploration, and the amine can be used as well to produce bicarbonate with diluted CO2 conditions. So just for a comparative purpose, the most utilized amine in the conventional carbon capture technology is monoethanol amine, 38%. So we're getting this loading 0.52 kilograms of CO2 per kilogram of amine, and with this surface active amine at the same conditions, we are producing 0.12 kilograms of CO2 per kilograms of amine. So, but in addition as well, our process is not releasing CO2. So we are not using this high energy process to release and regenerate the amine. So right now I'm going to talk about the bicarbonate separation and the amine regeneration, which is based on the electrochemical membrane-based systems. So as I introduced before, in order to work with the bicarbonate pathway, we have to change the way that we are capturing CO2 and the way that we are separating and regenerating this surface active amine. So as I mentioned, in this point, the separation and regeneration step, the bicarbonate is going to be separated from the capture solution, and the amine is going to be regenerated through this electrochemical process, and therefore, and then the bicarbonate is going to be free to be utilized to produce different chemicals. So by changing this method and implementing the surface active amine for carbon capture, we can we can highlight some advantages, which is this operation, the separation and regeneration, are going to be performed under ambient temperature and pressure. As well, at the same time, the bicarbonate is going to be separated, and And as well, one of the important thing is because it's an electrochemical process, we can utilize green electricity as an input or to drive this process, and that's also a really good point to mention. And as well, it's estimated 30% energy reduction compared to the thermal regeneration from what we have studied in the literature. So this is one of the points that I wanted to highlight, and how this separation and regeneration system or device works. So I'm going to go through the ion exchange membrane fundamentals first very quickly. So under applied potential, the different ions in a specific solution, it will move towards the opposite side of their charge. In this case, um, the negative ions will tend to move to the positive side of the cell, and the positive ions will go to the opposite side. So these devices allow us to move these ions through different membranes. In this case, the ion exchange membrane. This ion selectively transports the negative charge ions to the positive side, to the anode. And as well, for the positive ions, we have the cation exchange membranes. So it will transport this sodium, hydrogen ions, whatever ion that is positive. And as well, we have a third type of these membranes, which is the bipolar membrane. It's a combination of these anion and cation exchange membranes, and is primarily used to split water molecule into hydroxyl ions and proton ions. So how we're going to implement this technology in our amine regeneration and bicarbonate separation. So here is a diagram that explains better. So we have this capture solution. From after we complete the capture reaction, we have this solution that contains the protonated amine and the bicarbonate product. So we're gonna feed this into this electrochemical cell in this chamber. So the bicarbonate will be separated, will be moved towards the anode side through the ion exchange membrane. And as well, we can also introduce hydroxyl radicals to conduct the deprotonation of this protonated amine in an acid-base reaction. So at the end, we'll end up with the regenerated amine coming out from this membrane. And at the same time, we're going to be separating the bicarbonate into an adjacent chamber to collect this product and further be utilized for the conversion or the electrolysis step. Currently, the membrane-based systems are being explored increasingly, in particular for the CO2 capture area. So one of the things that I would like to mention is the majority of this publication of this or these studies are being used to what we call the catch and release process, which is basically utilize amine as well and perform the capture reaction, but then the product that they are collecting is CO2. So, and as well with this BPET system, they can perform the regeneration of the amine. But the main difference here is this they are releasing CO2 as the product. So in our case, the bicarbonate extraction or the separation has not been explored. So this is one of the challenging part for us, and as well one of the exciting points or for our motivation in our motivation to conduct this type of research. So therefore, I'm presenting the research objective, which is evaluate the performance of this electrochemically driven bicarbonate separation and amine regeneration using the ion exchange membrane systems. So I'm gonna present two main tasks, which is to determine the bicarbonate separation efficiency and the amine regeneration level using these ion exchange systems. And as well, the other main task is evaluate the energy consumption of this system that I'm going to present. So the experimental setup, as I mentioned before, so we have to conduct the CO2 capture first. And then we have to, once we have the carbon capture reaction completed, then we utilize our electrochemical system and to conduct the amine regeneration and bicarbonate separation. A picture is attached here below. And then the products, all the products that we are obtaining are being evaluated by carbon NMR and by titration method. So for these experiments, we have been using 100% CO2. It's just pure CO2. And as well, we have fixed volumes, fixed conditions, even the time. We are evaluating different parameters, which the more important or the main parameters that we are always considering are pH, conductivity, and current over all the experiments that we are conducting. And as I mentioned, a carbon NMR is being used to identify all chemical speciation during the process. And as well, to determine the bicarbonate concentration, we are utilizing potentiometric titration. So one thing here I would like to mention is we are, as I mentioned, we are utilizing carbon NMR and pH profiles to evaluate or validate the reaction, that the reactions are happening, because it's an acid-base reaction. So we have to account for the pH. It's a very important parameter to observe and analyze over the experiment. So typically when we have the unreacted amine, in this case is N9PO, we don't have the presence of bicarbonate and the pH of the solution is high. Amines typically are like alkaline solutions and the pH is around 12. When we perform the capture reaction, we generate bicarbonate. Therefore, the pH of the solution reduces around 7. So at this point, we have the mixture of the protonated amine and the bicarbonate. And then when we perform this amine regeneration and bicarbonate separation, we regenerate the chemical environment of the amine solution, and we get rid of this bicarbonate peak. The pH returns to its original value, which is around 12. So this is one of the process or one of the parameters that we are using to evaluate the reaction is performing the way we want to. And one of the things here is it's very useful for us to determine the regeneration of the amine, although we are using as well as instrumental characterization. So the first configuration that I'm gonna introduce is the single-step bipolar membrane electrodialysis. As I mentioned before, is because it's an acid-base reaction, we thought from the beginning what happened if we just split water molecule to produce hydroxyl radicals that is going to be in reaction with this with this protonated amine. So once we introduce here in the feed chamber, we will have bicarbonate ions and the protonated surface active amine. The bicarbonate ions will move through the anion exchange membrane to the adjacent chamber and leaving behind the protonated amine. So from this bipolar membrane, we're going to split the water molecule and generate the hydroxyl radicals. Then these two are going to react to neutralize the protonated amine. And therefore as well, we are utilizing sodium chloride to, we're introducing sodium chloride to our system to increase conductivity and provide as well sodium ions. So at the end of this process, we are gonna have the regenerated amine from this chamber we are going to have the product chamber. In this case, sodium bicarbonate is being formed, and as well we have an acid chamber where hydrochloric acid is being produced from this method. So one of the plots that are a typical plots that we are getting from these experiments is the pH profiles of the different of these different chambers. So for instance, the feed solution, as I mentioned, the pH, as the amine is being regenerated, the pH will increase uh, to its initial value, which is around 12. So we can observe over the time the pH of this feed chamber is being it's been increasing. That is also it's a good parameter for us that that the regeneration of amine is occurring. And another important parameter is the pH of the product chamber. In this case, this chamber where bicarbonate is being collected or being extracted to. And this pH is quite constant. That means the bicarbonate is being filled over there, and is not suffering any alteration from the system. So using this kind of configuration, we have simultaneous bicarbonate separation and amine deprotonation occurring in the same chamber here. So another way that we thought from the beginning of when we were designing these experiments was what happened if we split? Can we control the separation happening and the regeneration happening in two different chambers? So this is another configuration we evaluated. So the first cell is going to be only for separation, in which the capture solution is going to be fed, and then bicarbonate is just going to be extracted to this adjacent chamber. And the remaining protonated amine from the feed chamber is going to be introduced into a second chamber where is going to happen the acid-base reaction. In this case, we are using bipolar membrane to produce the hydroxyl radicals, and we get the regenerated amine from this chamber. So ideally, as I mentioned, ideally this will happen into two different chambers. However, if we can control these reactions by the experimental conditions, that's another that's another way that we are considering and exploring using one single electrochemical device or electrodialysis device. So therefore, for this if we have the splitted system, we can use a low potential condition. In this case, we can go very low, 3 volts, to drive this separation. And for the regeneration, so the water splitting reaction, it's a little bit more energy intensive than just driving the bicarbonate transport. So here we can ramp it up to 9 volts, and in that way, we can perform the water splitting and produce the acid-base reaction. So when we compare the performance of these two different systems, we can observe that having one single step or in a single unit driving both reactions, we can achieve bicarbonate separation and amine regeneration. Of course, as I presented the pH profile, we are getting up to 12. So and as well, we have conducted carbon NMR, and as well we have identified the amine is being completely regenerated. So the bicarbonate, however, is not the bicarbonate transport is not completely separated using this single step unit. However, as well, we were able to quantify the energy consumption of the systems, and as well comparing to the two-step system where we are separating or driving first the separation and then the regeneration. In this case, as the reaction happened more efficiently, so because we are just driving one reaction at a time, so therefore we can have we can achieve higher separation of bicarbonate from the capture solution, using less energy, 40% less energy compared to a single unit. And as this is one of the things that we have observed using these two different configurations. However, we are our target is to obtain lower energy values than one that are reported for the thermal regeneration, which I mentioned is around 4 megajoules per kilogram of CO2. So although we are in the way in our way to get there, what happens if we change or if we optimize our system and not only changing conditions, but what happens if we change the way that we separate the bicarbonate using different membrane arrangements. So and we thought about considering this, we thought about using pure hydroxyl source instead of the ones created by the bipolar membrane. So therefore, we propose this new configuration, the anion exchange enhanced electrodialysis system, in which we have two anion exchange membrane together or delimiting our feed chamber. So in this with this configuration, we are not using bipolar membranes. And as well, we are gonna reduce the energy consumption because we are not performing water dissociation reaction. And as well, we're gonna introduce sodium hydroxide, as I mentioned. So hydroxyl radicals are gonna move from this chamber into into the feed chamber to perform the amine regeneration. So in that way, we can have better control of the hydroxyl ions transport by modifying the concentration of the sodium hydroxide solution, and as well controlling through the potential of the cell. So this is kind of the mechanism for this bicarbonate, and the protonated amine will be fed into this chamber. The hydroxyl ions will come into this feed chamber, and at the same time we're gonna have the bicarbonate separation and the amine regeneration. So we will end up with sodium bicarbonate production and the regenerated or the deprotonated N9PO. So when we compare this new configuration, we observe something very interesting, which is we can achieve higher bicarbonate separation even compared to the bipolar membrane systems. So we are achieving 80% of bicarbonate separation, and as well we are reducing the energy, around 60% less energy compared to the thermal regeneration. So by these results, we corroborated that using these electrochemical ion exchange systems, using specifically these membranes, is useful to perform the bicarbonate separation from the capture reaction, and as well regenerate the amine utilized for the capture reaction with low energy consumption, even lower than the thermal regeneration. And finally, I'm gonna introduce some of the highlights for the electrochemical conversion. So here I'm just comparative right now in the literature, like the different electrolyzers that we can find reported by different research groups. The first one and the most typical, as I mentioned, is using a CO2 gas. So this is like the gas-fed CO2 electrolyzers. So for the conventional CO2 reduction reaction. So particularly here we are comparing the production of formic acid. So for this CO2 electrolyzers, we can achieve high Faraday efficiencies and high current densities, which are industrial relevant for this process. And as well, One of the limitation is we have low CO2 utilization, around 20% in a single pass conversion. So we have to recirculate all the CO2. And with these conditions, we can estimate around like the energy consumption of to produce 1 kilogram of formate around 5.85 kilowatts hours, which using these considerations, we can estimate $291 per ton of formate produced. So what happens if we compare like this conversion step? Instead of using CO2 gas, we use bicarbonate product into the same into a similar electrolyzer, but not using CO2 gas. So we are not handling any gas-related operation. That means the pressurized systems. We have higher carbon utilization, as I mentioned. We can work with higher concentrated solutions, and using these considerations as well, we can calculate around $130 per ton of formate. So which is considerably cheaper than using CO2 electrolysis. So the work that we are currently doing in the lab, it's we are working with the development of different electrocatalysts, particularly bismuth doped thin oxide electrocatalysts. We are using hydrothermal method to synthesize this material, and as well we are for the electrochemical reduction setup, we are exploring this reduction performance using an H-type cell condition. These are the more relevant parameters during the experiments, and we are, as I mentioned, we are exploring the incorporation of bismuth. We are studying through different instrumental characterizations. We are performing the fundamental studies for these different materials, and as well we are quantifying the formate generation through carbon NMR. So at this point, using this H-type cell, we are able to generate around 4 to 5 milligrams of formate per liter using these batch conditions. So, and as well, we have explored different ways of improving this performance. One of the most recent strategies we are implementing is to increase the pressure of the system, in which here in this image, for the different bicarbonate potassium bicarbonate concentrations with these lower pressure conditions, the species that are in higher concentration, although we increase the bicarbonate concentrations, it's carbonate, is dominantly carbonate species. So what happens if we have carbonate species all over the different all over the different range of bicarbonate? So by this reaction, this carbonate is the one that dominates, the species that dominates in this solution. So therefore, we are going to be using extra protons that as well comes from the reaction. So therefore, we are requiring higher energy. And this carbonate, in addition, is very hard to react to or to perform the reduction of this carbonate. So when we compare using a different pressure, so we can observe that bicarbonate is the one that dominates all over the different ranges of potassium bicarbonate. And from this reaction, we are utilizing only this proton from here, and the reaction another proton. So we have less amount of proton that we utilize for this bicarbonate electrolysis. So by using these fundamental differences, we were able to increase the Faraday efficiency of our batch system using the H-type cell. We improve around 32% by increasing this the pressure of the electrochemical cell, and achieving a total amount of 12 milligrams of formate per liter. So for this purpose as well, we are exploring, we're increasing as well the areas of the electrodes. We are using now nickel foams, and we are depositing our catalysts over here to perform these reactions in this way. So however, I would like to mention that one of the things that we are are actively working is to integrate all these three components of the bicarbonate pathway and explore these conditions in a single operation. So this is one of the things that I want to highlight. One of the biggest efforts of the research group and all the people working with these topics. So we are trying to integrate all the three steps into one single operation and evaluate many other things. So in summary for this presentation, uh, we demonstrated that the ion exchange membrane system can provide an energy efficient electrochemical alternative to the conventional thermal regeneration. And the key takeaways that I want you to have is the amine regeneration and bicarbonate separation can be conducted using both bipolar electrodialysis or just single electrodialysis systems. However, if we are trying to use a bipolar electrodialysis system, um, we observe that the two steps BPET system separates bicarbonate more efficiently. And as well, one of the things here is the amine regeneration is done. It doesn't matter the system that we are utilizing, if it's BPET or electrodialysis system, the amine regeneration is happening. The more limiting reaction is the bicarbonate transport. So therefore, this is this is the part that is taking a lot of efforts, research efforts for us to improve and optimize. And as well, our system, the anion exchange enhanced electrodialysis, requires 60% less energy than the thermal amine regeneration, achieving 80% of bicarbonate separation efficiency. So our next steps as a group, we are working as well to improve, as I mentioned, improve this bicarbonate separation process. So to achieve this task is we are considering different type of amine. We are exploring different types as we are working with different chemical structures for the capture part as well. We have plans to explore these different chemical structures for the bicarbonate separation. This includes as well the concentration of the surface active amine. That's one of parameters that we want to, at the time that we're integrating, integrate with industrial relevant conditions. So therefore, we have to utilize concentrated surface active amines, and as well variable CO2 concentrations as like the flue gas composition, or diluted CO2 concentrations like for direct air capture. And as well, one of the important things for us is to consider the chemistry of the membranes to enhance these transport properties. And as well, to include the techno-economic analysis for like the different system we are exploring, and as well as I mentioned, the integrated CO2 capture as bicarbonate pathway to integrate the three steps into one single operation and perform the techno-economic analysis once everything is connected. So finally, I would like to thank our sponsors that they have helped us to conduct this research, and as well to thank the group and Dr. Okuno, of course, for all the support for this research. So this concludes my presentation, and I will happy to answer any question. The first question is, could the electrochemical ion exchange membrane impact the chemical stability of the amine? So one of our experiments that we conducted using instrumental characterization, we have demonstrated, we have observed that the amine is totally regenerated, and even though we are using high potential, the amine is not being affected or impacted negatively by these conditions. And as well, with the pH profile or the pH increment or decreasing, the amine has been very stable. So we haven't observed any type of degradation. However, we would like to include different or additional characterization techniques to confirm what we have initially observed by carbon NMR. Second question is the electrochemical ion exchange method compatible with traditional monoethanolamine systems? Yes. Actually, one of the I mentioned that the bipolar electrodialysis system has been increasing, or their study has been increasing for in the carbon capture area. So they also have tested that monoethanolamine for this with this particular configuration. However, I would like to say that our system is not conducting any reaction in the system, so we are just transporting the ions. So for the MEA system, one of the main differences, we have to perform one of the reactions, one reaction to the amine to release the CO in order to release the CO2. So my point with this is, although it has been used for MEA, the configuration of the system will be different. So exactly our anion enhanced configuration cannot be utilized this way, but the membrane technology can be applied to monoethanolamine systems. Thank you for the time, and I hope this presentation it's interesting to you, and we are happy to talk a little bit more. If you have any question, you can contact us, and I will be happy to talk a little bit more with you.